So we were talking a little bit about tails, and I'm going to say a little bit more. We're going to do the tale about tails today. And let me talk about this. We're going to do the tale about tails for partial limits. And I want to remind you first what we mean by, for a given positive integer big N, what we mean by the big N tail of a given sequence, sequence xn. The tail is a set of numbers, not a sequence. This curly bracket thing is a set. It's the set of all the numbers you can get by looking at xn for any n greater than or equal to big N. In the event that big N is 1, this is the set of all the xn values you can get starting at 1. That's called the range of the sequence, the range. Please understand that if you make big N bigger, the tail gets smaller. If you take a larger value of big N, then there are fewer integers n that are greater than or equal to big N. See? The sequence of tails contracts. The 2 tail is a subset of the 1 tail. The 5 tail is a subset of the 4 tail. The 98 tail is a subset of all those that come before it. You see? And I said something that I'm going to repeat. A given sequence will be eventually in a given set S if and only if there exists a tail that is included in S. The statement that sequence xn is eventually in a set S is the statement that there exists an integer big N such that from now onwards and forever all the xn values are in S. What does that mean? The statement that the sequence is eventually in a given set S says that there exists an integer big N such that this set shown over here is a subset of S. That for every n greater than or equal to big N, xn belongs to S. That's this thing. This tail is a subset of S. A sequence is eventually in a set S if and only if there exists one of its tails that is a subset of S. And I want to do the tale about tails with you here for partial limits. There is also one for limits. It's not here. It's in the text. I told you it's not as interesting. It's also easier. And this is the more interesting one and slightly harder. And this is the one we need. And I want to talk to you about it. And I don't remember what I've said to you. And therefore, I'm assuming you don't know either. So I'm assuming I've said nothing, which is probably what I've said. I don't think I've done this. And let's see what we're looking at. Oh, by the way, I have to say this. I went very carefully through this yellow chapter 6. I noticed that there were a number of places where I had pasted in from the green chapter when I was writing this chapter. And in the green chapter, it's talking about sequences in a thing called a metric space. And very, very carefully, I eliminated all of those, and I made sure we're dealing with sequences of numbers and infinities and so on. And I didn't save the stupid document. And I created a new build of the book, where if you click for upgrade, it'll put you up to March 21. And I was fondly imagining that all those stupid references to metric spaces were gone. And I discovered to my horror yesterday only. Who was I with yesterday? No, I wasn't with you. I was with Jennifer. That's who it is. I have to work separately with Jennifer because of babysitting problems. And I discovered there's the stupid reference to a metric space over and over again. will you please, until we can get another update, if you ever see metric space, it's just sequence of numbers, okay? All our sequences. Don't panic here and say, what the hell is this metric space? One day, right? More abstract settings, wider topological settings, sure. And if it says, and X belongs to big X, X is a real number. Okay? That's all. I apologize. I rewrote them all, and then I didn't save the document. Shoot me, you know. What can I say? All right. So let me see what we got. We've got a sequence of real numbers and a number X. I rather fancy that if you look at this in the textbook, it may say a sequence in a metric space and a point X in the metric space. Just read it like this. And this is what your lecture notes will say. The following conditions are equivalent to one another. One, that the point X is a partial limit of the sequence. And two, that for every neighborhood U of X and every positive integer big N, something happens. I can't read it. Okay? Right. Proof that... Don't do that to me. What is going on here? Oh, it's because there's a numbered section. Right. Proof that condition 1 implies condition 2. Please do not mention implication, implies, except in a heading. There's a 99% probability that you are making an error if you ever refer to implication when you're writing in the body of a passage. And that applies to instructors as well. Listen to me. I'm an expert at mathematical language. And I'm not saying that of my own, I've been recognized as such. So I just want to tell you that. Now, and implies does not mean therefore. Now, proof that condition 1 implies condition 2. We assume condition 1. Reasonable? Tell you what, let's make this in a color. Okay? We assume condition 1. What do we assume? X is a partial limit of the sequence. Okay? We want to prove condition 2. We want to prove that for every neighborhood U of X, blah, blah, blah. Right? Suppose that U is a neighborhood of X. I know I've got to start like that. I have no alternative. I'm looking to prove for every, say, suppose. Lots of you are just not following that little thing. You write suppose statements without any reason to write it, and then everything goes wrong. And you say, well, Lewin always says suppose, why shouldn't I? He likes suppose. No, I don't. You've got to put it when you like it. And you've jolly well got to make sure you like it. If you want to prove that for every neighborhood U of X something happens, suppose that U is the neighborhood of X. Okay, now what do I need to prove? I need to prove that for every positive integer n something happens, right? Okay, well, I'll say suppose that big N is, suppose that big N is a partial limit of the sequence. This cord is driving me crazy. Let me see if I can get it underneath here. Okay. I don't know why they make it so short. Trying to strangle me. Okay. So suppose that big N is a what? A positive integer. It's because the chord was, that's my story and I'm sticking to it, is a, whatever it says over here, right? Over here, if it says a chocolate ice cream, I will write chocolate ice cream. It's whatever it says there is a positive integer. Right. Now I'm going to tell you. We know that the set of values of n for which x sub n belongs to you, we know that that set is unbounded above. I want to remind you, and you better know the definition. A number x is said to be a partial limit of a sequence if for every neighborhood u of x the sequence is frequently in u. Thank you, Michael. Right? Now, what does it mean frequently? A sequence is frequently in a set U when what? Sequence xn is frequently U when there are infinitely many values of n for which xn belongs to U. Right? So a set of positive integers is infinite if and only if it is unbounded. Right? And I'm looking at U. Infinite and unbounded don't always mean the same thing, right? But for integers it does. You see? Okay, you know what I'm talking about. Right? We had a conversation about that. So, the set of values of n, of positive integers n for which xn is in U, is an infinite set of integers if and only if that set of integers is unbounded above. Right. We know that that set is unbounded above. Well, therefore, I know that big N is not an upper bound, right? So I'm going to say choose N greater than big N such that x sub n, what am I doing, belongs to you. Isn't that, because big N is not, maybe I need to explain that. So big N is not an upper bound of this set, because there are no birds to fly. Okay? I told you. The word of is missing, huh? So now I'm saying, okay, big N is not an upper bound of the set. Choose N for which xn is in U and bigger than big N. And please note, just observe that this number xn that I have just referred to, following the word choose, this number xn, is in U, right? And it's in there, but now I'm going to change my mind. It's very bad for me to use the letter N of the alphabet here, because I'm using N as the dummy in there. So I think I'm going to choose, I'm going to use a different letter. Okay. J, K, you can use any letters that haven't been in use. Okay. Choose J greater than or equal to N such that x sub j is in U, and observe that this little xj is in U, and it's also here. Haven't I proved that that set is therefore non-empty? Because I have remember, I'm going to go through this proof again. We're assuming condition 1. I wish to prove condition 2. So what do? I want to prove that for every neighborhood U of x something happens. Suppose that U is a neighborhood of x. Then I say, now, what do I want to prove about this U? I want to prove that for every positive integer big N something happens. Suppose that big N's a positive integer. Now comes the crunch. we say, I know that the set of values of n for which xn is in U is unbounded above, because that's the statement that sequence xn is frequently in U. The set of values of n for which xn is in U is infinite. Alternatively, it's unbounded above, and so therefore big N is not an upper bound of that set. Using the fact that big N is not an upper bound of that set, choose an integer, and I very wisely called it by some name other than n, because then I can use n's in there. You know, you don't want to use the same symbol with more than one meaning. Math is hard enough if you don't do silly things. Such that the xj is in U, and notice that xj is in U, and it's also in that tail, you see? There it is. Right. Proof that condition 2 implies condition 1. Proof that condition 2 implies condition 1. We assume condition 2. I wish to prove that x is a partial limit of the sequence. What must I do to prove that that x is a partial limit of the sequence? I've got to prove that for every neighborhood U of x, sequence xn is frequently in U. Okay. Here we go. Suppose that U is a neighborhood of x. I'm going to change color for just a moment and tell you what I need to do. We need to explain why sequence xn is frequently in U. Isn't that what we have to do? I'm going to put my cards on the table. We need to explain, what does it frequently mean again? Why the set of values of n, the set of values of n for which x sub n is in U is unbounded above. Do you understand? What does it mean? The sequence is frequently in U. That the set of values of n for which xn is in U is unbounded above. I'm going to put a we need one more time. We need to prove that there are no upper bounds. Okay? We need to prove that every number must fail to be an upper bound of the set. The hardest thing is to type all this. See? Okay? All right. I think I'm ready. Let's come back to the color. Suppose that W is a number. Okay? Choose an integer, a positive integer, big N greater than W. Yes? Using condition 2, because we've assumed condition 2, isn't that right? If I'd been really kind, I would have said, we assume condition 2. I really should have written that. Got lazy. Using condition 2, choose n greater than or equal to big N, such that, such that x sub n is in U. Can't I do that? Look at condition 2. It says for every positive integer big N, there exists a value of n greater than or equal to big N, for which the xn is also in U. See? Well, we have found n greater than this W, for which x sub n is in U, and that proves that W is not an upper bound of that set. Let me say what I have to do. I want to prove that condition 2 implies condition 1. What am I assuming? What am I assuming for this? We're assuming condition 2. What do I have to prove? Condition 1. I'm assuming this. Now I want to prove condition 1. I want to prove that x is a partial limit of the sequence. What does that mean? Read it to yourself. Spell it out. What does it mean? X is a partial limit of the sequence. For every neighborhood U of X, the sequence is frequently in U. That's why I want to prove for every neighborhood U of X. Suppose that U is the neighborhood of X. Then I'm saying, okay, what do I need? I need to prove that the sequence is frequently in U. Ask yourself, what does that mean? You can't do anything if you don't know what the words mean. The sequence is frequently in U. That means that says there are infinitely many values of n for which xn is in U. Alternatively, that the set of values of n for which xn is in U is unbounded above. So how do you prove that set's unbounded above? You need to prove that every number must fail to be an upper bound. That's how I'm going to do it. How do you prove that every number must do something? Suppose that W is a number. Choose a positive integer n that's bigger. Condition 2 guarantees me the existence, and I choose n greater than or equal to big N, an n, one of these n's, for which xn is in U. And I've got a value of n greater than W, for which xn is in U, therefore W is not an upper bound. So that is the tale about tails for partial limits. So what's this 3 and 4? Let's just read it. Condition 2 says what? If you ever take a neighborhood of X and look at any tail, the neighborhood must intersect with that tail. Isn't that condition 2? I'm giving you the job of writing 2 implies 3, but I'm now telling you. You want to prove that X is close to every tail. Well, take a tail. Condition 2 says for every neighborhood U of X, U intersects with a tail. Therefore, X is close to it. You understand? Well, how do you prove that a point is close to a set? The statement that X is close to a set, for every neighborhood U of X, U intersects with a set, right? So here, in condition 2, what do I know? I know that whenever you take a tail and a neighborhood of X, these two intersect. Isn't that what it says? So look at a tail. For every neighborhood U of X, U intersects with that tail. Therefore, for every tail, X is close to the tail. Okay? The other direction is the same thing. If you know that X is close to every tail, then if you ever take a neighborhood of X and a tail, they have to intersect because X is close to the tail. If U is the neighborhood, it's going to hit the tail. It's really quite simple. The connection between 3 and 4 is easier. When you look at 4, it scares the hell out of you with all this. But let me tell you that this notation over here, just that, that's the set of numbers that are close to the tail. Isn't that right?
The closure of the set.
Yeah, the closure is the set of points that are close. And you know what the intersection means? You belong to the intersection when you belong to every one of the sets. saying that x is in every one of these is exactly saying that for every big N, x is close to the set, the tail. Belongs to the closure of the tail means is close to the tail. You see? All this number 4 is saying is that for every one of these sets there's a guarantee that x belongs. For every one of the tails, x is in the closure. For every one of the tails, x is close to that tail. So I haven't written exactly every little bit. The textbook might have a little more than what I've given, but I've given you enough that you do some writing. Okay? That's where it is. And now we're going to do something that I've been itching to do all the time since we began limits, because we've been having to use strange language. Limit of a sequence. Well, let me tell you what's going on here. We assume that x is a limit of a given sequence, sequence xn, and that y is unequal to x. We are going to prove that y cannot also be a limit, cannot also be a limit of sequence xn. One of the reasons why you don't write notes in my lectures is that I have the right to change what I have. This is initially what I'm saying. We assume that x is a limit and the y is unequal to x. And we're going to prove that y can't also be a limit. What would this theorem say? That if a sequence has a limit, it has only one. What do you want to call it? The Highlander theorem or something, right? So I'm going to do better than this. This is the statement I wrote for you. It's not the statement I'm going to prove. Not only am I going to prove this, I'm going to take out the word also. Cannot be a. I'm going to tell you something. If you assume that x is a limit of a given sequence and y is unequal to x, not only can y not be a limit, it doesn't even get in the ballpark. It's not even a partial limit. You understand it's easier for a number to be a partial limit than to be a true limit. You understand? So I'm saying here, if x is a limit, any other extended real number doesn't even get to be a partial limit. I'm telling you that if you ever have a sequence that has a limit, that limit is the only possible limit, and as a matter of fact, it's the only number that can even be a partial limit. You understand what this is saying? I'm telling you that when a sequence has a limit, it can't have more than one partial limit even. The limit is, of course, a partial limit, but no other number can be. So a sequence that happens to have a limit will not have more than one partial limit. So if you look back at any of the examples we've seen in the past, where 1 was a partial limit and 4 was a partial limit, you can be quite sure that sequence can't have a limit. See? If there's more than one partial limit, there can't be a limit, if you believe this theorem. Before I prove this theorem, I want to tell you what I've not said. I haven't said to you that if you got a sequence and you are guaranteed that there cannot be more than one partial limit, that therefore there must be a limit. What have I said and what have I not said? assume that x is a limit of a given sequence. This sequence has a true, honest-to-goodness limit x, and I want to tell you that any number other than x can't be a partial limit. The only possible number in the extended real number system that can be a partial limit is this number x, so there can't be more than one. What I've not said is that if you have a sequence and you are guaranteed that there is not more than one partial limit, then it's got a limit. That's what I've not said. But just for the heck of it, who thinks that's true? Who thinks it's false?
I don't know enough to say either way.
You've got a sequence, and I'm giving you information. This sequence does not have more than one partial limit. Conclusion, then it must have a limit.
What if it doesn't have any partial limits?
What if it doesn't have any partial limit? Yeah? Good point. But can that happen? Can that happen? What do you think? I'm going to raise this. Well, if the sequence is unbounded above, it jolly well does have a partial limit. Haven't I shown you in this course? Haven't we done together that when a sequence is unbounded above, infinity must be a partial limit? I hope we did that. Did we? I hope I did it. I want to make sure that I did it in here, not anywhere else. Joshua, have I done that? Okay, right, because I know that I didn't speak to you anywhere but in here. That's why I picked on you. Okay? So if a sequence is unbounded above it, definitely there's an extended real number that's a partial limit. And if the sequence is unbounded below, then minus infinity be a partial limit. So Julie raised the question, what if there's no partial limit? Well, that sequence is bounded. What if a sequence is bounded? It's in a box. It's buzzing around inside a box. I actually posed this once before, and I asked you to vote on it. I said, if you've got a sequence that is bounded, then there must be at least one partial limit, or maybe not. Maybe Lewin is going to come up with a sneaky example of a bounded sequence, and it's going to bounce around inside between a lower bound and an upper bound, and somehow it won't ever have a partial limit. And I asked, what did you think? I got more votes for sneaky example than for the positive statement. What do you think? Sequence. Got a sequence. Besides your example wouldn't have worked. You want a sequence that bounces around. Can it fail to have a partial limit? Or do you think somehow if it's trapped and it's bouncing around, it's trying to get out of the cage and it's bouncing around, it's going to pick up a partial limit in there? Who thinks there will be? Who thinks that I'm going to come up with a sneaky example? I got more votes for sneaky example last time. Right? There's got to be a partial limit. That's a major, major fact. And in fact, it's one of the key ingredients of where we are heading in this chapter, and eventually it is the key to the big facts about differential and integral calculus. Believe it or not, very important. So therefore, let me tell you, a sequence can never fail to have a partial limit. If it's unbounded above, infinity works. If it's unbounded below, minus infinity. If it's bounded, we'll find one. Today? Hell no. But we'll do it before the term ends, in spite of the snow. Okay. So therefore, I've done with your objection. What if there is no partial limit? There is. Okay. Folks, what do you think? If a sequence cannot have more than one partial limit, therefore it's got to have a limit. What do you think? Who's voting no? I think I've got some no votes. Who's voting yes?
It has to have a limit.
If a sequence cannot have more than one partial limit, it will have a limit. I've got very few people who would vote. You don't want the humiliation of me telling you you're wrong, right?
I'm leaning towards
You know how many times I've been wrong?
I'm leaning for that one being true.
I've got one vote yes and one vote no so far. Everybody else? Anybody want to cast a deciding vote? Who's waiting to see which way I vote? You think that my vote counts for anything? Mathematics is not very democratic. If I vote wrongly, I'm wrong too. But anyway. You'll vote no. I've got 2 no's and 1 yes. I love teasing you. And the answer is to be like these TV shows and then they bring commercials, right? The answer is yes. If a sequence cannot have more than one partial limit, there will be exactly one, and that one and only one partial limit will be a true limit, but we can't do that today. What we're doing today is a much, much easier fact. If you know that x is a limit and y is unequal to x, we're going to prove that that y can't be a partial limit. Now look here, either y is less than x or y is greater than x. We are going to assume that y is less than x. The two cases are mirror images of one another. You could write case 1, case 2, but you could say, look here, the other case is a mirror image. Or you could say the other case is homework. I don't know. I'm assuming that y is less than x. By the way, I want to mention something. I said that y is unequal to x, so of course either y is less than x or greater than x, but if I am dealing with a case in which y is less than x, I hope you understand that in this particular situation, there is no way for x to be minus infinity. You understand? Y might be minus infinity, I don't care. And x might be infinity, but y, of course, couldn't be infinity. Or they both might be just real numbers. X might be a real number and y is a smaller real number. Okay? And this is how we go. Choose. When are you allowed to say choose? You say choose when you know that something exists. I'm about to choose something very easy. Choose a number w such that y less than w less than x. Now, in the event that y is minus infinity and x is some number, I could just define w to be x minus 7. If either x or y is one of the infinities, it's particularly easy. But what happens if y and x are real numbers? Suppose y and x are real numbers and y is less than x. Aren't there numbers between them? Actually, we know even better than that. In an earlier life, we proved that there are even some rational numbers here. Not that I care, I don't need a rational. I'm just reminding you that we did that. A bunch of numbers here. How about the average, the arithmetic mean, y plus x divided by 2, if you really want to do something silly, you see? Okay, choose a number w between them. The set w infinity is a neighborhood of x, is it not? That's a neighborhood of x. And so, sequence xn is eventually in here. Do you understand? Now, when a sequence is eventually in a set, it cannot be frequently in the, finish my sentence. Finish my sentence. And there should not be a single person not finishing this sentence. When a sequence is eventually in a set, it cannot be, what? Frequently in the complement. Right. So I now know sequence xn cannot be frequently in this interval. Isn't that right? Cannot be frequently there, which is a neighborhood of y. You understand? Well, I have in my pocket a neighborhood of y in which the sequence refuses to go frequently, so y can't be a partial limit, and that's the end of the proof. Because using the fact that x is a limit, I made a conclusion. I said the sequence xn must be eventually in the interval w infinity. Where did I write that? Here. The set of numbers less than or equal to w, and I've actually taken a slightly smaller set of numbers less than w. There's no way the sequence can be frequently there because it's eventually in the complement. You understand? So here I have a known neighborhood of y, and the sequence is not frequently there. Therefore, the y can't be a partial limit. That's the uniqueness theorem. If a number, an extended real number, this fixes the infinities and everything. You want to rewrite this for the case in where x is less than y, it's the same argument. Choose a number, w, between, you just be careful which way you write these intervals. See? Look at the picture. Okay, folks? That's the uniqueness theorem. At this point, the limit notation, I want to tell you, the lim notation is now permissible. Why? Because if a sequence has a limit, how many does it have? One. So now you can give it a name. You can call it Rumpelstiltskin, or lim of n of xn, or whatever, all these standard Calc 1 notations. You may now use that notation. You could not until this moment. A sequence xn is said to be, here's a word, and it means the same thing here as it meant in elementary calculus. Convergent. When what? When sequence xn has a limit, and the limit is not either plus or minus infinity. It's got to be a real number. It's got to have what we call a finite limit. Okay? And I've got a heading, boundedness of convergent sequences. I'm going to make a statement here. Every convergent sequence must be bounded. Every convergent, what does that convergent mean? That the sequence has a limit, and the limit is? The limit is not plus or minus infinity. Okay? And I claim that such a sequence must be bounded. I cannot remember what I wrote in the text. Here is a slick method that you may feel is too slick. And I'm not writing this, I'm saying it. You're going to write it. We assume that sequence xn is convergent. The limit of sequence xn is a real number. No other number, extended real number, can be a partial limit, right? That includes infinity. Can't be a partial limit. The limit is some number, a real number. You call it Charlie, okay? And that Charlie is not infinity. You understand? It's not minus infinity. So any other number can't even be a partial limit. So infinity is not a partial limit. So the sequence is bounded above. And minus infinity is not a partial limit. So the sequence is bounded below. Therefore the sequence is bounded. I rather tend to think that in the textbook I reinvented the wheel and gave you a direct proof from scratch. I cannot remember. But if the sequence has a limit and the limit's a real number, that real number is the only possible partial limit. So neither plus infinity nor minus infinity can be partial limits. So the sequence can't be unbounded above and it can't be unbounded below. So it's bounded. There we are. And the next thing is the sandwich theorem. The sandwich theorem is used quite a lot in Calc 1 for functions, and in fact is critical when we get the trigonometric limits that are used to do the calculus of the trig functions. One thing that always drives me absolutely up the wall is when people walk into Calc 2 or Calc 3 and they've allegedly done Calc 1 and they can recite d dx of sine x is cos x. And I discovered that the student has not the first foggiest clue why. And I'll tell them, you know what, you haven't had Calc 1. You recite that. And you can use the product rule. You can say d dx of x squared sine x is 2x sine x plus x squared cos x. And you think you've done nothing. Your ability to say that and crunch out from the product rule and find the volume of the box and find that turning point of the graph. And if you don't know why the derivative of sine is cos, you have to repeat Calc 1. Maybe somebody was busy with some MyMathLab garbage and forgot to teach you any calculus. You say, oh, well, he mentioned something, but everybody knew it wouldn't be in the exam. Yeah, then it wasn't mentioned. Students are smart. If something isn't going to be in the exam, they turn off. They've got lots of things to do. You should rather say less when you're teaching, cover less, and whatever you cover, cover. That's the way, it's the correct way to teach. Don't pretend. Yeah? Limit notation can be used from the moment that we've proved the uniqueness theorem and not 1 nanosecond before.
Okay, so only proofs after this point? We can't go back?
If you use a limit notation when we don't yet have the uniqueness theorem, you're talking nonsense. How can you name something if there could be 5 of them? Which one gets the name? Can't do that.
Are you saying going back and doing those earlier problems now? That we have this?
No, you can't. Those earlier problems are part of the development before, unless you're very careful, then you have to check the proof of the uniqueness theorem and check that it doesn't make use of the earlier problems. That's a big responsibility. Make sure you're on top of stuff before you do that. It's possible that you could handle it, but just be careful. There's a danger. Then the sandwich theorem. The sandwich theorem, I'm stating it for sequences. Let me tell you what we are assuming. We assume we are given 3 sequences. Should we call them sequence xn and sequence yn and sequence zn? Okay? 3 sequences. And we are given the inequality. We are given the inequality that says that x sub n is less than or equal to y sub n less than or equal to z sub n for all n. Okay? Finally, we are given that x is a real number and that the limit as n tends to infinity of xn and the limit as n tends to infinity of zn are both equal to the number x. When I write this, it means it includes, we are given that sequence xn has a limit, and the limit is this number x. We are given that sequence zn has a limit, and the limit is, are you pressing buttons on an electronic machine? In my classroom, that is an absolute no-no. There are no electronic machines in this room. Two things that I don't want here: electronic machines and paper. The paper only if you're using it to stay awake. Okay. Now, I'm sorry to make myself difficult, but I'm only looking after your interests. We are given that x is a real number, and that the sequence xn has a limit, and the limit is x. And the sequence zn has a lit, and the limit is x. We can prove that sequence yn will have a limit, and the limit is x. This is called the sandwich rule, sometimes called the sandwich theorem. Some people call it the squeeze theorem. Squeeze. You want to squeeze the sandwich, the peanut butter comes out. All right. So we're going to prove this thing. Are you ready? Here's the proof. In order to prove that sequence yn converges to the number x, in other words, that sequence yn has a limit, and the limit is the number x, I've got to prove that for every neighborhood u of x, sequence yn is eventually in u. Isn't that what it says? But I've already told you that for practical purposes, when you're working with a limit and a real number or whatever case, it's actually easier to work with intervals and sticks than with arbitrary abstract neighborhoods. Haven't I told you that? When I wrote the definition in several ways, I said it's actually, and when we did some of these little applications with rational functions and 1 over n's and stuff, we used deltas and epsilons and things instead of neighborhoods. I'm going to do the same thing. Suppose that epsilon is greater than 0, and I'm going to let you know I am trying to explain to you why. Well, I'll say this. I need to explain why sequence yn, that one, is eventually in there. Do you understand? Think of the definition, folks. What does the definition say? So many people try to memorize a bunch of working steps and it goes nowhere. Think what the definition says. The sequence has limit x, if and only if what? For every neighborhood u of x, that sequence, its name is sequence yn, is eventually in u. Alternatively, for every stick center x with positive radius, the sequence is eventually in there. Suppose that epsilon is greater than 0. That's my job. Right. I'm going back to this field using the fact that sequence xn is eventually in the stick. We choose an integer called big N1 such that the condition x sub n belonging here will hold for every n greater than or equal to, can't make big N, 1. This keyboard is wobbling, and this, I wish they'd give me a decent table. This table is one I brought in, and now they think they don't have to bring one. Do you see what I did? I said, I know that sequence xn has got to be eventually in that stick. Choose big N1. From now on, from big N1 and forever, the xn is in there. Now I'm going to tell you something else. Using the fact that, who knows what I'm going to write? Using the fact that sequence Zn is eventually in there, choose, what did I do? Choose what? Choose begin to such that the condition Z in here, that condition holds, what am I going to say? For every n greater than or equal to? Begin to. Now what happened? Not J. Begin to. What am I going to do? What? Well, I want to make both of these statements hold, don't I? This is my strategy, is to force both the xn and the zn into the stick. How do you do that? The xn gets in from big N1 forever, and the zn gets in from big N2 forever. So define big N to be the larger of big N1 and big N2. Right? For every n greater than or equal to big N, well, that n will certainly be greater than or equal to big N1, and it will also be greater than or equal to big N2. So let me tell you what we have. X minus epsilon has to be less than xn, because xn is in the stick, right? Xn is less than or equal to yn, given, which is less than or equal to Zn, given. And Zn is in the stick, so Zn has to be less than x plus epsilon. So, this is what you mean, gotcha. I've caught you. You are trapped in here. From big N on, look, Yn is in the stick. You see? We see that sequence Yn must be eventually in that stick. See? I want to say to you that the way in which this works is that for large enough n, the xn can't be much less than x, and the zn, can't be much more, and the yn is trapped between them, so it can't be much less, and it can't be much more, so it's got to be close. That's the nature of the proof. Okay? So let's try, which exercises do I want? I want to do number 12. I'm going to be stopping very soon, but I want to do just a little bit here. Number 12. We are given, let me get rid of the Skype. I don't even know who that is. Not even a clue. Luis? Oh, is that? Quit Skype. Go away. Right. I need the Skype because I have to call Galen. Right? I'll switch it on again. So now, in number 12, we've got two sequences, called sequence AN and sequence BN. And AN tends to a number A and BN tends to B, and A is less than B. Prove that there exists an integer big N such that from now and forever AN is less than BN. And this is how the exercise works. Choose, very similar in nature to the proof of the uniqueness theorem. choose a number q such that A is less than Q is less than B. Picture, here's a picture. Here's A, and here's Q, and here is B. You understand? Okay. Now, the sequence must be eventually below Q. Let me tell you. Using the facts, I can't remember how I write. UTFT, that's what it is. Using the fact that sequence AN is eventually in this. How do you know? How do you know that sequence AN must be eventually in there? Because that is a neighborhood of A, because Q is bigger than A, right? And sequence AN converges to A, right? Therefore the sequence, right? Choose big N1 such that A sub n will be less than Q for every n greater than or equal to big N1. Did you follow me? The next thing I'm going to tell you is using the fact that, I can't believe I couldn't remember how to make using the fact that. Using the fact that sequence Bn is eventually in this interval. How do you know that's true? This interval is a neighborhood of B, is it not? And B is a limit. Choose big N2 such that B sub n is greater than Q for every n greater than or equal to big N2. See? Reasonable? Yeah, define big N2 be the larger, I'm not writing it, the larger of big N1 and big N2. For every n greater than or equal to big N, we have both of these inequalities. That will guarantee that AN is less than BN. Okay? Do you have to do the problem this way? I can think of a few other proofs. This, I think, is easiest. Don't ever feel that you are pushed to write exactly the proof I wrote. I'm going to suggest to you, here are some other ways in which I see this in some of the books. Assuming that A and B are real numbers, you could say define delta to be 1/2 the distance from A to B. And you take the delta stick around A and you take the delta stick around B. Lots of books do this. I find that clumsy. It's messy. Much easier. Choose the number Q between them, below, above. Neighborhoods of A and B. You get in there, and you go beyond both begins. Okay? Write it. Have I done all these exercises? No, I haven't. I may decide to do a little bit more, and I may not. I'll probably do at least one more of these on Wednesday before we move. I can't promise to do every exercise. I've got to leave something for you. Okay? And that's all I have to say today. And it shouldn't have been a very hard lecture. I hope not.